Constitutional isomers slash structural isomers, they have the same molecular formula but different connectivity. So for example, this is pentane. It has just 5 carbons with enough hydrogens on them to make them stable, and it's just in a straight line. But this is 2-methylbutane. It's got the same number of carbons, the same number of hydrogens, 5 carbons, 12 hydrogens. It's all the same as this N-pentane, except it's just got different connectivity. There's a methyl group on the number 2 carbon instead of just a straight chain. Now, it's easy to see that these are not identical, that they are isomers of each other, but it's not as easy to see that these two drawings are identical. We can know that they're identical because in both cases we have 2-methyl butane. We have a methyl group on the number 2 carbon in both of these cases. So these are identical, they have the same connectivity. A carbon on the number 2 carbon. We also have geometric isomers. They have the same molecular formulas, but they also have the same connectivity in that they have the same number of atoms of each element on certain other atoms. Only the atoms are around different areas or regions around certain atoms. So for example, take a look at our dibromo trans ethene. In this case, we have bromines on opposite ends of this carbon-carbon double bond. Now, in the previous case here, we saw that with having carbon-carbon single bonds, there could be easy rotation around each carbon. This bromine could end up down here, as you see in this depiction. But that's not the case when we have carbon-carbon double bonds. These are 120-degree bond angles that are not able to rotate. They're rigid. And so this bromine cannot end up down here. This bromine will be on an opposite end of this bromine. So we call this trans. So we also have, excuse me, we also have this other version. This is a geometric isomer of that trans version. It's cis, because the bromines here are both on the same side of the carbon-carbon double bond. And they'll be stuck on the same side because there is no rotation about here. Now, later on, you might wonder if this molecule is the same as this. They don't look the same right now, but you'll see that the bromines are both on the same side as each other. These are both cis versions of this alkene. One way to know that these are identical is to just rotate this in your mind. So if you just kind of flipped this whole thing around, that was actually not very good. Let me try that again. If you flip this whole thing around so that the bromine was here and this bromine was here, the bromines would still be on the same side, and you'd see that the depiction is the same as this case here. So just another way to know that these are identical is that they have the same name. They're both cis versions of the alkene. Okay, scrolling down, let's talk about resonance. We've talked about this in regular AP Chem, regular general chemistry, where we might have a negative charge on this oxygen, but that negative charge is stabilized over this system because it doesn't just exist here, but it exists on this carbon a little bit and this oxygen a little bit. We can tell what other resonance forms we have by moving electron pairs. You can move an electron pair in to form a bond, which forces electrons off of this carbon. This carbon, a period 2 element, cannot have more than 8 valence electrons around it. So if you're going to be forming a new bond near it, you're going to have to break this old bond, and the electrons in it will have to move up onto this oxygen. So you can see the other resonance form here. Now, in this case, both of these resonance forms are equally stable because we have the negative charge on an oxygen in both cases. And we also have full octets in both cases, and the same number of bonds. But to know whether certain forms are less stable than others, or more, we need to track all those things again here. Like, for example, yes, we have about 1,000 to 1 degree of importance of this group versus this group. This is another resonance form of this carbonyl, but this one is much more important because it's got more bonds and less formal charge. It's got full valence shells, so you can see that here. We've got 4 bonds instead of 3, and we have no formal charge instead of a negative charge on the oxygen and a positive charge on the carbon. So you can draw other resonance forms, but you'll know here that the more stable one, and the one much more representative of reality, is the one with more bonds, full octets, and less charge. Of course, if there is a charge, it's better to have a negative charge on more electronegative elements and positive charge on the less electronegative elements. Okay, and finally, just want to make this clear. Elements that are period 2 elements cannot have more than 8 valence electrons around them. So for example, because we saw up here that the carbon couldn't have an extra bond here and 2 bonds here and another bond here, have 10 valence electrons around it, we had to move this electron pair up. All right, thank you for watching, guys.